Welcome back to the deep dive. Today we are looking at something that, on the surface, looks incredibly boring.
It does look dry, doesn't it?
And I mean that in the most literal sense. We are looking at a stack of engineering paperwork.
A few PDFs, some charts, a lot of numbers. You probably just scroll right past it.
Right. We have what we're calling Document A, which is this very slick, high-tech report. It was generated by a piece of software called SkySieve.
Right.
It's got 3D renderings, heat maps, tables of data that go down to like the third decimal point. It looks like the kind of thing you pay a lot of money for.
It looks authoritative, like the final word on the subject.
Exactly. And then we have Document B.
Which is the reality check.
It's an email, a short, sharp internal memo from a supervisor that basically takes that beautiful, expensive report.
And just tears it to shreds.
It's a complete forensic demolition.
It really is. And that's why we're talking about it today. Because this isn't really about engineering, or at least not just about engineering. It's about what I'd call the glossy trap.
The glossy trap. Explain that.
It's the idea that if a computer generates a result and it presents it with perfect formatting and these incredibly precise numbers, then it must be true.
We just accept it.
We do. Our brains are wired to see that precision as truth. But what we're looking at here is a fundamental clash between a simulation that claims to be perfect and the messy physical reality of how gravity and wind and steel actually work.
Okay, so let's set the scene. What's the mission here?
Well, the project context is right there in the job setup. It's
Classic infrastructure job.
Yep. Overpasses, concrete, heavy steel. The kind of stuff that holds our world together.
And there's a very specific engineering challenge they're trying to solve. They need to design for positive Z direction wind load.
Which sounds technical, but it's pretty simple.
It's just the wind, right?
It's just the wind. Positive Z is just coordinate talk for the wind is blowing directly into the face of this wall we're building.
And we can see the key players involved. We've got the designer, an who's an EIT, an engineer in training.
So, likely a junior engineer.
And then we have the reviewer, the supervisor who wrote that critical email.
And the tension between them, or at least between their documents, really gets at the heart of this big theme. The complexity of a 3D model versus the reliability of a simpler 2D one.
So let's start with that digital blueprint, the SkySieve report, Document A, because honestly, if you handed this to me, I'd probably just sign off on it. It screams competence.
It's designed to. It's titled EFCO Wind Positive Z DIR WL 4 Sample 01. The software version is listed, SkySieve Structural 3D V7.1.1.
That sounds impressive.
It is. It's a top-tier cloud-based structural analysis platform. It's not something you run on a pocket calculator. This is serious, expensive software.
And the level of detail is frankly a bit overwhelming. Let's look at the job setup section to get a sense of what we're actually building here.
Right, the physical reality of the model.
It defines a plate size of 4 feet by 24 feet.
So to help you visualize that, think of a billboard, a tall, skinny billboard, 24 feet high, that's about 2 stories, and 4 feet wide.
Okay, I can picture that. And then there's the wind pressure. It's listed as 16.7 PSF.
Pounds per square foot. Which, again, as a number, 16.7 doesn't sound that scary.
No, it doesn't immediately jump out. But then the report helpfully translates it for us. It says, velocity, 81 miles per hour.
81 miles per hour. Let's just pause on that for a second.
That's a lot.
That is not a breeze. That is not a windy day. That is a severe gale. It's bordering on hurricane force. If you were standing in an 81 mile per hour wind, you wouldn't be standing for very long. You'd be tumbling down the highway.
Okay, so this massive, massive force is hitting this 24-foot-tall steel sail. The engineering challenge is pretty obvious. How do we keep it from tipping over?
Exactly. You need a support structure. And the report lays out the bill of materials very clearly.
It does. The main spine of this thing is called Section 1, the EFCO Super Stud 07.
The hell's intense, right? Super stud.
It really does.
It's a workhorse of heavy construction formwork. It's a very stiff, very strong steel beam. That's the main vertical part, the 24-foot mast of our sail.
And then to prop it up, to keep it standing, we have Section 3, which is listed as HS102 by 6.4.
Which is just engineering shorthand. It stands for a hollow structural section. Basically, a round steel pipe, about 4 inches in diameter.
So these are the braces.
These are the braces. So picture that vertical super stud, and like you have these diagonal pipes reaching from the stud back to the ground, acting like kickstands.
And the geometry seems pretty standard. The report lists all the node coordinates.
Right, the points in space where everything connects.
We have node 221 at the bottom at y equals 0, and node 469 at the very top, y equals 24 feet.
The full height of the structure.
And then these braces connect at different heights. Member 1 connects a node way in the back, node 8 up to a point high on the stud, node 55.
It creates a triangle.
Exactly. Member 3 does the same thing lower down. It's a triangle.
And triangles are good. Triangles are strong. On paper, the geometry makes perfect sense. It looks like a completely standard formwork support system you'd see on any job site.
And this is where the software really does its magic. It runs what's called a linear static analysis.
It just means it's doing the math.
Right. It crunches the number on the weight of the steel itself, which is about 0.706 kips, so 700 pounds or so.
Yep.
And it calculates the force of that 81 mile per hour wind pushing on it. And then it spits out the results.
The perfect result.
I'm looking at the displacements table right now. This table tells us how much the wall actually moves when that huge wind hits it. And there's a number here that just jumped right out at me.
Let me guess. The member 2 displacement sum.
That's the one. The movement of the main vertical beam, it peaks at roughly 0.077 inches.
0.077.
That is less than a tenth of an inch.
Just think about that for a second.
Yeah.
You have a structure that is 2 stories tall. It's being hammered by an 81 mile per hour storm.
A near hurricane.
And the computer, this incredibly sophisticated piece of software, says it moves less than the thickness of 2 credit cards stacked together.
My immediate reaction is, wow, that's an incredibly solid wall. Great design.
And that right there is the trap, because your reaction should be, wait a minute, that seems physically impossible.
Impossible? Why? Steel is really strong.
Steel is very strong, but steel is also elastic. It has give. It bends. Everything bends. If you have a 24-foot tall beam, even a braced one, and you hit it with that much force, it's going to deflect. It might not break, but it will definitely move.
More than 0.077 inches.
A lot more. That number suggests a level of stiffness that implies this thing is carved out of a single, solid block of diamond, not bolted together from construction pipes on a roadside.
But the report is so precise. It doesn't say about 0.1. It says 0.077. That precision, it implies a level of accuracy that makes you afraid to question it.
That is a perfect description of false precision. The software calculated the math correctly based on the inputs it was given, no question. If the world actually worked the way the input said it did, then 0.077 would be the right answer.
But the inputs were wrong.
The inputs were a fantasy.
So let's talk about those inputs. Because the supervisor, in document B, spots the error immediately. And they use a word that I think is going to be the theme of this whole deep dive. Fixity.
Fixity. It sounds like a made-up word, but in structural engineering, it is everything. It's the whole ballgame.
The email says, and I'm quoting here, there are still some errors with the simple models. In particular, it is your wind loading model that has fixed points in it that cannot be fixed.
Okay, so to understand this, we have to talk about how things connect to other things in the real world.
Okay.
Let's use an analogy. Imagine you are holding a broomstick, just standing it upright on the floor.
Got it. Holding a broomstick.
If you just hold it lightly with your fingertips at the top, and I come along and push the middle of the broomstick, what happens?
The stick rotates around my hand. My hand stays still, but the stick pivots.
Exactly. Your hand is supporting the stick, but it is not stopping it from rotating. In engineering, we call that a pinned connection or a released connection. It allows for rotation.
Okay, that makes sense. Pinned.
Now, second scenario. Imagine you take that same broomstick and you bury the bottom end 2 feet deep in a bucket of quick dry concrete.
Okay. It's solid now.
It's solid. And then I come along and push the middle of the stick. What happens now?
It doesn't rotate. The whole stick bends.
Right. The connection itself is rigid. It fights back against the rotation. It transfers that push into a bending force along the whole length of the stick. That is a fixed connection.
So fixed means rigid, welded, glued, locked in concrete, and released or pinned means hinged, bolted, free to pivot.
Precisely. Now let's go back to that glossy SkyCiv report. Look at the members table. You'll see 2 columns called Fixity A and Fixity B.
I see them.
These are the codes that tell the computer how each end of the beam connects to its node. Is it buried in concrete, or is it held by fingertips?
And for member 1, that's the upper brace, it lists the code FFFFF.
6F. 6Fs. And for member 2, the main stud.
Also FFFFFF.
And those 6 letters correspond to the 6 degrees of freedom that exist in a 3D world.
Okay, I know X, Y, and Z, that's 3 dimensions. moving left, right, up, down, forward, back.
Right, those are translations. But you can also rotate around the x-axis like a propeller. You can rotate around the y-axis like a spinning top. And you can rotate around the z-axis like a pinwheel.
So 3 translations, 3 rotations, that's 6.
That's the 6. So F means fixed in that direction, and R means released.
So when the designer typed FFFFF, they told the computer, this connection is fixed in all 3 directions of movement, and D, it's fixed against all 3 directions of rotation.
They didn't just tell the computer it was buried in concrete.
No.
They told the computer it was a magic, infinitely rigid joint that cannot move, twist, or turn in any dimension whatsoever. It's a point of absolute, immovable stability.
But in reality, on the actual job site.
On the job site, these are steel pipes connected with pins or bolts or clamps. They're designed to be like the broomstick in your fingertips. They're supposed to pivot. That's how a simple truss structure works. The members are designed to take tension or compression, but not bending.
So because the designer selected fixed, the computer model assumed the joint itself was fighting the wind.
That's exactly. The computer's logic was, oh, I don't need to bend the beam very much because this magic joint is absorbing all the rotational force.
It's like the joint became a superhero.
It did. It magically absorbed the energy into this fictional fixity. That is why you got that ridiculously small 0.0077-inch displacement. The model was cheating gravity.
And the really scary part is, the report hides this so well, you have to know what FFFFF means to even spot it.
Well, you do and you don't. The supervisor spotted it another way. And this is where the real detective work comes in.
Wow.
They looked at the pictures. Specifically, they looked at the bending moment diagrams.
The blue curves shown in the report.
Right. There's a screenshot in the document, SM102.jpg. It shows the bending forces on that main 24-foot beam.
It looks like a snake. It curves one way, then it crosses the center line, curves the other way, then crosses back again.
That S-curve, that snake shape, is the unmistakable fingerprint of a fixed connection. It physically shows the ends of the beam grabbing it and twisting it back against the wind.
So what should it look like if it were done correctly?
If it were pinned like it should be in reality, it would look like a simple billy or a smiley face. The wind pushes the middle bows out. One simple, clean curve.
So the supervisor didn't even need to dig through the tables and check the FFFFF code. They just looked at the shape of that blue line and knew instantly that's wrong.
Exactly. It's an intuitive check for an experienced engineer. A 24-foot beam that's pinned at the bottom and propped up somewhere in the middle should deflect in the simple curve. Seeing that snake shape is like watching water flow uphill. You know instantly that the physics engine has been given the wrong rules to play by.
And that brings us to the whole 3D trap, because the supervisor's feedback isn't just, hey, fix this code. They make a much broader point about the dangers of even using 3D software for this kind of problem.
This is the part of the memo I absolutely love. The supervisor writes, it represents a two-dimensional problem being modeled in 3 dimensions.
And they mentioned that this same designer, Hoke, did another model, a concrete pressure model, in 2D, and that one was fine.
Right, and they explain why. Your concrete loading model is much easier to understand as there are a lot less degrees of freedom.
Okay, so why is 2D safer? My first thought is that 3D would be better. It's more realistic, right? The world we live in is 3D.
The world is 3D, that's true. But many engineering problems are best understood by slicing them into 2D. Think about it. In a 2D world, on a piece of paper, you only have 3 things to worry about. Movement left and right, that's X. Movement up and down, that's Y. And rotation on the page, that's rotation around Z. That's it, 3 degrees of freedom.
It sounds much more manageable.
It's very hard to screw that up. You pin the bottom, you put a roller support at the top, done. But the moment you open SkySift 3D, you are suddenly wrestling with 6 degrees of freedom. You have to worry about movement in and out of the page, the Z-axis, and you have to worry about rotation around the X-axis and rotation around the Y-axis.
And the supervisor nails it. It is easy to pick the wrong one.
And this very report proves the point. Just look at the supports table. It's a mix of codes. We have FFFFR for some of the support nodes.
So fixed, released. 5 Fs and an R.
Try to visualize what that means. Which axis is released? Is it the rotation around Z? Is Z the vertical axis or the horizontal axis in this particular software's coordinate system?
The report calls it positive ZDIR-WL, so Z must be the wind direction, I think.
See, we're already getting confused, and we're just talking about it. Imagine you're the junior engineer staring at this screen, trying to toggle these little check boxes. Wait, do I release rotation X or rotation Y? If you click the wrong one, you might accidentally tell the computer that the beam is free to spin like a propeller, or conversely, that a connection that should pivot is locked up solid.
It's complexity for the sake of complexity.
It's like using a Ferrari to drive to the mailbox at the end of your driveway. Not only is it complete overkill, but you're actually more likely to scratch the paint than if you just walked.
There's a specific line in the memo that was a little confusing at first. The supervisor says, if they were based on this and have fixed members, then they would be more stable, as that would be the pipe braces welded to the super studs.
Right, what they're doing there is explaining the physical reality of what the designer's fixed model actually implies.
So they're saying if I actually went out to the highway overpass and I got a welding torch and I welded those pipe braces to the studs, really fuse them together, would the fixed model then be accurate?
It would be more accurate, yes. If you weld a joint, it becomes rigid. It can resist a bending moment. So if you actually built it that way, the structure would be incredibly stiff. It might actually deflect only 0.077 inches.
But nobody builds temporary formwork that way?
No, of course not. This stuff is temporary. You put it up, you pour the concrete, and you take it down a week later to use on the next job. You don't weld it, you pin it. You use clamps and bolts. So modeling it as a welded structure is incredibly dangerous because you are predicting a strength and stiffness that simply will not be there on the day of the pour.
So if they'd built it based on this report?
Well, the report says everything is fine. Stresses are low, displacement is negligible. So maybe think, okay, we can use lighter bolts, or we can space these support beams further apart to save money.
You make economic decisions based on this flawed data.
Exactly. Then the 81 mile per hour wind hits. The real joints, which are pinned, not fixed, rotate freely just like they're supposed to. The beam deflects way, way more than 0.077 inches. The geometry changes, the system becomes unstable.
And it falls down.
Potentially. Or it deforms so much that the concrete formwork blows out, spilling wet concrete all over the highway. Best case, you lose a lot of money and time. Worst case, something collapses.
All because of a setting, a checkbox, in a software menu.
All because the engineer stopped thinking about the physical reality of steel and started playing a video game called Sky Civ.
I noticed one other little inconsistency in the report that seems to hint at this confusion. Right at the top, in the job setup, under general constraint, it says RRRR.
Right. The default setting for all members. All released.
But then when you get down to the specific supports table, it overrides that default with things like FFFFFR.
This is a classic sign of someone fighting the software. My guess is they probably ran the model with the default RRR first.
And what happened?
The model was unstable. It fell over. Because if every single connection is a frictionless pin, the whole thing is just a pile of loose sticks. The software would throw up an error message. Model unstable.
So they panicked.
They probably thought, oh no, my design is wrong. But instead of checking the design, they started changing the model's assumptions. You start locking things down, you go to a support node, you click fixed, you run it again. Okay, now it runs, I get a result.
You constrain the model until the error message goes away.
You've nailed it. You torture the data until it concesses. But by over-constraining it, by locking down those nodes just to get a result, you created a model that is stable math, but it's fake physics.
So how do we fix this mess? Section 4 of our outline is the path to correction. And the supervisor doesn't just say, you're wrong. They offer a clear solution.
They do. They offer two paths, actually. Option A is you can attempt to fix your third model by adjusting the nodes.
Which means going back in, finding all those Fs, and carefully turning them into Rs in exactly the right places.
Which is very risky. You have to be perfect. You have to know exactly which axis allows for rotation and which doesn't. You can easily make another more subtle mistake.
Which leads to option B, which the supervisor explicitly calls preferred.
Start over and build a second model.
And then there's this fantastic quote, you don't need a 3D model.
It's such a relief to hear a senior engineer say that. There's so much pressure on young engineers today to use the fanciest tools, to show off the cool 3D rendering in the meeting. But the supervisor's saying, stop. Go back to basics. Draw it on a napkin if you have to.
Because in 2D, the problem becomes simple again. The wind is just an arrow pushing from the left.
And the beam is just a line. And the ground is just a triangle support. You can't get lost in the z-axis if the z-axis doesn't even exist in your model.
There's also a really interesting management lesson here at the end of the memo. The supervisor says, for now, just update one model and send it back. Don't go and update everything.
That is such smart management. The job description, remember, was for sample 01. The implication is that there are many other samples, maybe sample O2, sample O3, for different wall heights or wind zones.
Right. And if the junior engineer had run off and fixed all of them at once,
They'd probably just make a different mistake on all 10 of them. The supervisor is being methodical. They're saying, prove to me you understand the physics on one single example. Let's debug your thinking process, not just the file. Once you get the concept right, then you can apply that lesson to the other models.
it's the strategy of iteration. Don't try to scale up until you have a proven working prototype.
Exactly. And it limits the damage. If you fix one and get it wrong again, we've only wasted an hour. If you fix 10 and get them all wrong, we've just wasted an entire day.
You know, what really strikes me about this whole story is the timeline. The report is dated January 16th, 2026. This is now. This is, for all intents and purposes, the present day. We have AI, we have cloud computing, we have these incredibly powerful tools, and yet the ultimate solution is go back to 2D.
It's a paradox, isn't it? As our tools get more powerful and more complex, the need for fundamental human intuition actually goes up, not down.
Why do you think that is? You'd think the tools would do the thinking for us.
And that's the danger. The tools can do the math. SkyCiv calculated that matrix of forces perfectly, but the tool has no common sense. It has no feel for the material. It doesn't know that a temporary brace on a construction site isn't welded. Only a human knows that.
So the computer gave us a displacement of 0.077 inches. An experienced human looks at that number and says, hang on, that's too small. That doesn't feel right.
Right. A human who has stood on a windy job site knows that things shake, things rattle, things move. A wall that deflects less than 1/112th of an inch in a near hurricane. That's suspicious. The computer doesn't have suspicion. It only has inputs and outputs.
That phrase used earlier, false precision. I keep coming back to that.
It's one of those dangerous things in the modern world of data. If I told you the answer to a problem was about 5, you'd probably double-check my work. You'd feel comfortable questioning it. But if I tell you the answer is 5.038, you assume I did the work. You assume I know something you don't.
The decimal points act like a shield against criticism.
They do. They shut down inquiry. And the supervisor's job, and really our job as critical thinkers in any field, is to look past the decimals and just ask the simple question. Does the shape of this make sense?
The snakes versus the smiley face.
Exactly. Forget the numbers for a moment. Just look at the curve. Does it behave like a stick being pushed? Or does it behave like some kind of magic snake?
So let's try to synthesize all this. We started with a report that looked absolutely perfect. I+ work, send it to the client.
And we discovered it was actually a very detailed, very precise map of a place that doesn't exist in the real world.
We learned about the concept of fixity, the difference between holding a broomstick with your fingertips versus burying it in 2 feet of concrete.
And we learned how confusing the code FFFFFF for concrete and RRRR for fingertips can be when you're staring at a complex 3D coordinate system.
We saw the glossy trap, the seduction of the beautiful 3D model, and the precise computer-generated answer.
And in contrast, the wisdom of the 2D solution. How simplification is not stupidity. Often, simplification is the only path to clarity.
And finally, the human element. The hero of this entire story isn't the billion-dollar software. It's the grumpy supervisor who took one look at that snake-shaped graph and had the experience and the confidence to say, nope, that's wrong, and send the email.
Absolutely. The software is just a very powerful calculator. The engineer is the one who has to decide what to calculate and whether the answer makes any sense.
So here's the thought I want to leave everyone with as we wrap up. We are all using black boxes in our lives now. Maybe it's a finance app that's predicting your retirement portfolio. Maybe it's a health tracker on your wrist telling you how well you slept. Maybe it's just a GPS telling you the fastest route to work.
We trust the output because the screen is shiny and the numbers are precise. The GPS says it will take 27 minutes, not about half an hour.
But how often do we stop and check the fixity of those assumptions?
That's a great way to put it. Is the GPS assuming I can drive 60 miles per hour when I know there's always construction on that road? Is the finance app assuming the market is fixed and will grow at a stable 8% when I know it's volatile?
Are we assuming stability where there is actually freedom of movement? Are we assuming a fixed point where there should be a pin?
That's the question. Don't let the algorithm turn off your intuition. If the graph looks like a snake when your gut tells you it should look like a smiley face, trust your gut, not the machine.
Check your notes, people, or the wind will check them for you.
Beautifully put.
Thanks for diving in with us. We'll see you next time.